Okay. Walid, you can start recording.
Yes, thank you.
Okay. So we'll talk about string theory today. Before we start, we'll follow the book String Theory in a Nutshell, which is by Elias Sis, I think. Yeah. So I'm writing the name of the book. Uh, So, before we talk about string theory, we'll talk about the history of physics today. Okay, so I don't think we have enough time to go to the technical part of string theory. So, let's start with the history of physics. So there are two quotes in the book that I really like. So the first one is the quest in physics has been historically dominated by unraveling the simplicity of physical laws, moving more and more toward the elementary. And the other quote is the other organizing tendency of the human mind is toward unification. So uh, what is unification means? So unification means finding a unique framework for describing seemingly disparate phenomena. Okay, so in physics, there are two instincts that are very important. Okay, so we'll talk about two instincts. The first one is reductionism. So by the name, we can understand reductionism means breaking matters into smaller pieces. Okay. So if we break an atom, that will gives us matter into smaller pieces. And the other driving force in physics was unification. So unification is basically explaining different phenomena with one framework. Uh, like uh, if we study electricity and if we study magnetism, so uh, in one singular framework, we can define electromagnetism, right? So uh, these two instincts is the main reason why we study physics. Okay, sometimes these two instincts cooperate, and sometimes they conflict. So one example of cooperation is electromagnetism, which I have just said. So in electromagnetism, let's say we're talking about, sorry, magnetism. So in electromagnetism, reduction works as, so we have many electric and magnetic phenomena. So like sparks, magnets, currents, lights, etc. And unification. So uh, by Maxwell's law, we can see that this all these phenomena are are generated by one field, which is the electromagnetic field. So Maxwell shows they are all one field, which is the EM field. Okay, so uh, here both the reduction and unification cooperate, right? And we have another example where we can see that sometimes reductionism and unification conflict. How? So another example will be the point particle and the gravity. So reductionism says go smaller, which is the point particles, and unification. So unification, we are including gravity with quantum mechanics. So here we can see some conflicts. So the conflicts are point particles. So it shows that probe arbitrarily small distances and gravity couples to energy. So these small distances creates huge energy fluctuations, and this results in non-renormalizable infinitives. So what we're seeing here is reduction, which is points, destroys unification. So here the unification is quantum gravity. Okay, so uh, sometimes these two instincts cooperate, and sometimes these two instincts conflicts. Okay, so before we advances to another thing, uh, I'm asking you a question. So, which instinct dominates particle physics today? Can you say me? Which one dominates particle physics? Reductionism or unification? Anyone?
I think reductionism.
Yes, exactly. So in modern particle physics mainly focuses on reductionism, right? So uh, we can see LHC searches for new particles, then precision measurements of quark masses and couplings, flavor physics and CP violation, etc. So reductionism is the main focus of today's particle physics. But we want to talk about string theory, right? So naturally, we want to talk about unification. So why modern physics is not focused around unification? Well, unification exists, but they are not experimentally dominant. Okay, so we have some theories, which is the grand unification theories. So grand unification theory, so this is still not experimentally confirmed. We have supersymmetry, which has not yet observed. Then quantum gravity. So this is far beyond experiments. But still, we want to talk about unification. So, uh, so I'll give you just a brief history of unification in modern physics. Okay, so we'll talk about the major unifications. So, in the 19th century, Maxwell unified electricity and magnetism. So, they arise from electromagnetic field. In the early 20th century, Einstein unified spacetime and gravity. So this is called general relativity. So general relativity is classical, still no quantum mechanics involved. Okay, so this is classical. Then in the 1920s to 40s, we have quantum mechanics. So, so, Quantum mechanics is developed, but gravity is left out. So gravity is left out in quantum mechanics. Okay. And by 1940s, we have electromagnetism and quantum mechanics, which is quantum electrodynamics. And after 1940s, in the 1950s and between the 1950s and 1970s, we have Gates theory revolution. So between 1950s and 1970s, we have so in gas theory, forces arise from local symmetries. So this local symmetries is called gauge invariance. So um, and this gauge theory results in weak plus electromagnetic, which is electroweak theory. And the strong force gives us quantum chromodynamics. Which is QCD. So these theories are all quantum and they're renormalizable and they are based on the gauge groups. Okay. So by the early 1970s, there's a new theory arises from all of the previous ones, which is the standard model. Okay, so by 1970s, we have standard model. So standard model, so this theory says that um, so standard model is built from three independent symmetries, okay? And each symmetry gives rise to a force. So we have three independent symmetries, which is SU3 and SU2 and U1. We have three independent symmetries, and each of them gives rise to a force. Um, so let's talk about the gauge group. So gauge groups are basically a set of symmetry transformation that do not change the physics, but force the existence of interactions. Okay, so gauge groups are a set of symmetry transformations that do not change the physics, but force the existence of interactions. So we are saying that these three different gauge groups are independent, and each of them corresponds to a different force. So these different forces are, so SU3 gives us strong force. So this is strong force acts on quark color. Let me write it down. So acts on quark color and gives rise to gluons. And this strong force describes QCD.
Uh, I
Yeah.
had a question.
Yes.
Like for those of us who have not done particle physics, like SU2, SU3 just means like special unitary groups to us. Like, can you
Yeah.
explain briefly how like a group relates to a force, or like how these, why are we calling these gauge groups?
Uh, okay. Mm, so basically, these groups are basically symmetry transformations, right? Uh, Sorry, can you ask the question again?
Uh, Like I have not done particle physics, so I am not like I,
Yeah.
I I cannot make the connection like how a group gives a force. Can you just like uh, is there any mechanism or anything this like uh, for me a group is just like that follows the definition of group, and why are we calling this a gauge group, and how that like gives a force?
Uh, Mauser.
So when you have a symmetry,
Yeah.
okay, so you have, let's say, a gauge symmetry, you have a gauge field, right? Right, gauge field থাকে, right? Like
Mm-hmm.
let's say electric potential or whatever, okay? Like A0, A mu or whatever, okay? A0 would be what, phi or whatever, the electric potential. So so a symmetry leads to a gauge field. Like a gauge field, so once you introduce a gauge field, you need to make your action invariant. So that means you have to introduce like the a mu into the whatever derivatives. Becomes like a like a covariant derivative. Okay, so like a mu plus I a or d mu plus I a mu. Okay, right? But often then okay, so then in the you get when you multiply everything together, you get like something like psi. Let's say for a like a fermion, psi a mu and then psi or psi bar a mu psi. That means you get an interaction. Okay, so once you include the gauge field into the action, you get interactions which involve the gauge field. Those interactions are, I mean, interactions generate forces. So you can do whatever, or you can calculate the scattering diagram with those interactions, and you get like what the interactions basically are at long distances, and those are like those are the forces. Well, actually, so the interactions lead to these forces. Does that make is that helpful?
Yeah. I think I got a like, overall mechanism like how the from the
So
group we get forces.
group from a group you get a connection A
In
or a
yeah,
gauge field.
Okay.
mm,
The gauge field leads to an interaction. Interaction
interaction
leads to
gives
the force.
yeah, yeah. Okay. So yeah. So next we have SU2. So SU2 gives weak interactions, which is weak force. So this acts on weak isospin. So isospins. So isospin is a quantum level that tells us how a particle participates in the weak force. Okay, and this SU2 is responsible for beta decay, and this involves W and Z bosons. And we have U1, which is electromagnetism. This acts on electric charge and gives rise to the photon. And this is the simplest symmetry among the other two. So, so why this is called the standard model? Uh, so this is called the standard model because it explains all non-gravitational particle physics. So SU3, SU2, and U1. This gives particles like fermions, which are quarks, leptons, which has spin half. Then we get the gauge bosons, which has spin 1, and we get the Higgs particle, which is spin 0. Okay. So each of these gauge groups gives us a force, right? Sorry. So each of these groups gives us some force, uh, but there is one force missing in the standard model, and that force is the gravity. So standard model. So so we can see that there's a problem in standard model. We are not getting gravity. Gravity is geometric, which is basically the space-time curvature. And standard model forces are gauge fields on space-time. Uh, yeah. So when we try to quantize GR like other forces, uh, we'll get, so when we try to quantize we get non-renormalizable infinities. Also, there is predictive power loss. And uh, we can see that the standard model is non-consistent in high energy theory. So we can see that there are some problems in standard models. So let's discuss these problems a bit broader. So let's talk about the conceptual problem of standard model. So the first thing, so we're seeing that uh, even ignoring gravity, standard model is kind of unsatisfactory. Why? Because we can see that uh, there are three um, there are three separate gauge factors, and gravity is completely separate. Okay, so this is not an experimental problem. Okay, uh, let be so uh, this uh, this is not a not an experimental problem. A standard model works extremely well. It is a theoretical dissatisfaction that why three groups? Why not two or three or five? Okay. Uh, so in Maxwell theory, we can see that we have only one symmetry and one force. And in electroweak theory, you see unified SU2 and U1. So the standard model feels patched together, not inevitable. Okay. Um, and these three gauge groups gives too many parameters, which gives many masses. There's a problem with the mixing angles and couplings looks arbitrary. And there is a problem called hierarchy problem. Uh, let's talk about this hierarchy problem. So in fundamental physics, there are two important scales. So the first one is the electroweak scale, and the second one is the Planck scale. Okay. Uh, so electroweak scale is set by the Higgs mass, and this is roughly 100 gigaelectrovolt. Uh, and this scale controls masses of W and Z bosons and also masses of quarks and leptons. And in the Planck scale, this is set by gravity, and this is roughly 10 to the power 19 gigaelectrovolt. And in this scale, quantum gravity becomes important. So you can see that the Planck scale is enormously larger than the electroweak scale. Okay, so the hierarchy problem is so if we compare these masses, you can see that uh, there is a gap of 10 to the power 17 order of magnitude. Okay, so we're getting a very large number. So in nature, uh, large number is not a problem. The problem is the stability. Okay, so we have a problem with the stability. And if you study quantum corrections, so in quantum field theory, particle masses receive quantum corrections. So what is this quantum correction? So in quantum field theory, we not only get bare masses, we also get some quantum corrections. Okay, uh, so a mass of a physical object is equal to the bare mass plus some quantum correction. And this correction depend on how high in energy the theory goes. Okay, so for Higgs boson, the quantum correction goes like so delta mh squared, which is approximately lambda square. Okay, so here lambda is a cutoff scale. And if we set this cutoff scale by the Planck scale, so if the cutoff scale is Planck scale, then we have mh squared 10 to the power 19 GeV. So if we set the cutoff scale by the Planck scale, this becomes 10 to the power 19 GeV. But experimentally, we have found that mh is approximately 125 GeV. Okay, so there is a problem. So we're getting a smaller physical Higgs mass by experiment, right? So by experiment, mh is approximately 125 GeV, but in Planck scale, the mh is around 10 to the power 19 GeV. So what is happening here? So to get a very small uh, physical mass, so here we are getting uh, uh, so to get a very small physical mass, we are starting with a huge bare mass. So the bare mass is very huge, and we have a very huge quantum correction. Okay, so we have an extreme fine tuning here, and this feels unnatural. So we are only talking about the mass of Higgs, right? So what about the masses of other particles. So while other particles don't suffer like this. So the fermions, let's say fermions, we have electrons, quarks. So they are protected by chiral symmetry. Uh, so, sir, can you explain a bit about the chiral symmetry? I have some confusions about this.
But are there any questions of what chiral symmetry is? Chiral symmetry is just left-handed and right-handed.
The right-handed, yeah.
That they're treated differently, that's all.
Yeah, so left-handed particles can be rotated among themselves, and same right-handed particles can be rotated by themselves without affecting any physics.
And so,
So,
but
yeah,
there's a preference for handedness in the standard model. So the mass terms, they kind of like couple right and left together, so they kind of break the chiral symmetry.
yeah,
Um, so I think that's enough for now.
okay. And the gauge bosons, they are protected by the gauge symmetry. So we can see that Higgs has no such protections. Yeah. So hierarchy problem so the hierarchy problem, why it is a problem? So not because the standard model is wrong, but a fundamental theory should not require absurdly precise cancellations with no explanation. Okay, so there are some rescue attempt to save standard models. The first rescue attempt is the grand unified theory. So in standard model, we see that there are three gauge groups. And the grand unified theory proposes that instead of three unified groups, we have one group, and from that one group, we are getting these three separate gauge groups. So this tells us at very high energy, the strong weak and electromagnetic forces are actually the same forces. And at low energy, they only look different. So how this unification theory works? So at low energy, which is, let's say, today, forces look different. At high energy, which is, let's say, early universe, the symmetry is larger, and all the forces merge. So instead of three separate gauge groups, grand unification theory proposes we have one simple group, let's say, which is SO5 or SO10 or E6. Okay. So instead of having these three separate groups, we have only one larger group. And at low energy, this big symmetry breaks into these separate symmetries. Okay, so why SO5 or SO10 or E6? So these groups are not chosen arbitrarily. They are highly constrained. Okay, um, and we're choosing these groups because this contain the standard model symmetries, and that they can fit quarks and leptons together, and they are mathematical.
I think you're inaudible. আচ্ছা ভাইয়া, আই থিঙ্ক ওয়াইফাই বন্ধ হয়ে গেছে সামথিং, মানে সে রিজয়েন করার ট্রাই করতেছে।
আচ্ছা, কারেন্ট চলে গেছে হয়তো ওরা।
Hello, am I audible?
Yes, yes, you're
Yeah,
now
sure.
audible.
Okay.
Okay. Mm. Yeah, স্ক্রিন দেখা যাচ্ছে কি?
হ্যাঁ হ্যাঁ, সব দেখা যাচ্ছে।
Okay. Okay. Let's start. So the grand unification theory works with coupling unification. Coupling unification says that each force has a coupling strength, and these strengths change with energy. So when we extrapolate them to very high energy, in standard model, they almost meet. And in the grand unification theory, especially with supersymmetry, they meet very neatly. Another success that the grand unification theory has, which is predicting sine square theta w. So here, theta w is the weak mixing angle. This is also known as the Weinberg angle. So let's talk about this weak mixing angle a bit. So in a standard model, one field, one natural field comes from SU2. This is usually called W3. And another natural field from U1. This is usually called B. So nature does not use W3 and B directly. Instead, it forms two linear combination. We have two linear combination of W3 and B. So one combination is photon and the other combination is Z bosons. So this mixing is exactly like rotating axes in geometry. Okay, so if we have two axes, y and x and y, and if we rotate them by an angle theta, we'll get two new axes, right? And uh, the original axes are represented by W3 and B. And if we rotate this axis by theta W, Uh, so we'll have some new uh, new combination, which is photon and Z boson. So photon and Z boson basically tells us how much each original field goes into the photon and Z bosons. Okay, so ground unification theory predicts this mixing angle uh, because uh, this sine squared theta w measures how electromagnetic like or weak like a particle interaction is. So at low energy, so around the z mass, sine square theta w is approximately 0.23. So this is measured experimentally, and this is very experimentally precise. In standard model, sine squared theta w is a free parameter. Okay, but in grand unification theory, sine squared theta w is predicted. So by grand unification theory, we're naturally getting these mixing angles, where in standard model, sine squared theta w is basically a free parameter. So sine squared theta w is a measurable number that tells us how the electromagnetic and weak forces are mixed into the photon and Z bosons. Okay, so this is a successful thing that we are getting from the grand unification theory. So another success we're uh, getting from the grand unification theory is that in standard model, quarks and leptons are unrelated. So in standard model, quarks and leptons are unrelated, but in grand unification theory, these two sit in the same multiplet. And this explains charge quantization and similar patterns across families. Okay, so we can say that we have some success in ground unification theory, but still we are missing gravity, and we have talked about the hierarchy problem. So in ground unification theory, the hierarchy problem worsen because uh, ground unification theory introduces very heavy particle, and this push the cutoff limit, which is delta. Uh, this cutoff limit, ground unification theory pushes this cutoff even higher because we are getting heavy particles. So this makes Higgs mass instability even worse. And we have also some experimental issues in ground unification theories. So prediction like proton decay have not been observed yet, right? So this is not still completely uh, unified theory we can go with. Okay, so in the late 1970, there is a second attempt to rescue the standard model, which is called tech Technicolor. So Technicolor proposes that what if Higgs does not exist? Okay, so this theory proposes Higgs does not exist as a fundamental particle at all. Okay, so Technicolor replaces the Higgs field with a new strong force that generates mass dynamically. So this proposes introducing a new strong force. So this strong force called Technicolor, and introduce new fermions called technifermions. And these fermions bind together due to the strong force. And their condensate breaks electroic symmetry and gives masses to W and Z bosons. So this is exactly what the Higgs does, but without Higgs, Higgs particle. Okay, so there are some advantages of Technicolor. So in Technicolor, because no Higgs mass problem, we have no fundamental scalar, and everything generated dynamically. So this feels natural and QCD-like. But despite this success, uh, Technicolor has some problems. So these problems are Technicolor gives fermion masses. So this gives masses to electron quarks and turn out to be very difficult without ruining other physics. And also there are some flavor problem with Technicolor because Technicolor predicts large flavor changing effects that experiments do not see. We have a problem in the precision data. Electro weak precision measurements. So which is called Z physics. Electric precision measurement strongly disagree with Technicolor prediction. Okay, so Technicolor tried to eliminate the Higgs by using a new strong force, but failed because it conflicted with the experiment. So, and after this theory, we have a third attempt to um, to revive standard model, which is the supersymmetry. So this is done by late 1970s and late 1980s. So we have talked about two big problems. The first one is the hierarchy problem. And in standard model, unification looks close, but not exact. Okay, so not exact means coupling strengths almost meet at high energy, but not perfectly. So we have two problems. One is the hierarchy problem. And unification is close, but not exact. So to solve this problem, the physicist at that time proposes that there may be a new symmetry that we are missing, and this symmetry is supersymmetry. Okay, and supersymmetry is a symmetry that relates fermions and bosons. So more concretely, we're saying that supersymmetry tells us every fermion has a bosonic partner, and every boson has a fermionic partner. So standard model particle. So for electron, so electron is a fermion, and the partner of this fermion, the supersymmetry partner, is s electron, which is a boson. For quark, this is also a fermion. The supersymmetry partner is s quark. This is a boson. for photon, this is a boson. The partner is photino. This is a fermion. And for gluon, this is a boson. The supersymmetry partner is fluorino. This is fermion. ওকে, আচ্ছা, আমরা কি কন্টিনিউ করব নাকি ক্লাস আছে তোমাদের কি এখন?
আমার ক্লাস আছে একটা, আই থিঙ্ক। যদি শেষ না হয় আমরা আবার যে কি দুইটার দিকে আবার রিজিউম করতে পারি যদি সবাই ফ্রি থাকে।
আচ্ছা,
আমার ক্লাস আছে 2টা থেকে 5টা পর্যন্ত।
আম, আচ্ছা, আমরা
পরশুদিন or something, পরশুদিন?
হ্যাঁ স্যার, টিউসডে সমস্যা নেই কোনো।
Tuesday এমন টাইমে I can do 11 works.
পরশুদিন বলতে টিউজডেতে?
অথবা আজকেই
আচ্ছা,
পাঁচটাতে আবার করতে পারি আমরা।
আচ্ছা, আজকে পারবো না, বাট আজকে মানে শুনতে পারবো, বাট I mean হ্যাঁ, ক্লোজলি শুনতে পারবো না প্রবলেম।
আজকে
ওকে ওকে।
আমারও আচ্ছা, আজকে আমারও প্রবলেম, আমি আবার দিনাজপুরে যাচ্ছি আজকে। সো কালকে বা পরশুদিন কি পসিবল সকালে 11টার দিকে?